Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 1st, 2026, about 5 days ago. It introduces a training-free framework that achieves state-of-the-art quality in 3D morphing, enabling smooth transformations between completely unrelated objects, such as a bee and a biplane. The paper is titled MorphAny3D, Unleashing the Power of Structured Latent in 3D Morphing. And, as we'll see later, the ability to maintain structural coherence without heavy training is quite significant. And for those interested in the implementation, the authors have shared their code on GitHub. So Figure 1 presents a gallery of these morphing sequences to illustrate the results. Each row tracks the evolution from a source object on the far left to a target on the far right. Take the bottom row, for example, where a bee morphs into a biplane. Notice how the organic wings transition seamlessly into mechanical ones. Or look at the third row from the bottom, where a character transforms into a tree. These examples demonstrate the method's capacity for smooth transitions between completely unrelated categories. Well, while the previous gallery looked seamless, Figure 2 reveals the difficulty of the task by comparing 4 different strategies for transforming the source on the left to the target. The first row shows matching-based morphing, which often collapses into a scattered, noisy mess of geometry. Row B tries morphing in 2 dimensions first, which creates plausible individual frames but fails to stay consistent over time. Then, row C uses direct interpolation, which is stable but structurally weak. Finally, the bottom row demonstrates MorphAny3D, which successfully maintains a clean, plausible character throughout the entire sequence, earning it the happy emojis on the right. Alright, having seen the results, Figure 3 breaks down the architecture. Panel A maps out the full pipeline, processing input images to generate the 3D structure. The key innovation appears in Panel B as morphing cross-attention, which blends source and target features to ensure structural coherence. To keep motion smooth, Panel C introduces temporal fuse self-attention, borrowing information from the previous frame. Finally, Panel D illustrates orientation correction, which actively rotates the model to prevent sudden, jarring spins. So, with the architecture defined, Table 1 quantifies how well it actually works compared to existing methods. The comparison tracks metrics like Fréchet inception distance for visual quality and perceptual path length for smoothness. MorphAny3D achieves the best scores across most categories, notably dropping the Fréchet inception distance to roughly 1.12, which is significantly lower than the baselines. Crucially, looking at the last 2 columns for aesthetic score and user preference, the method dominates, securing over 86% of the user preference vote, while most competitors struggle to break single digits. Okay, while the previous table showed the metrics, Figure 7 provides the visual proof across 3 distinct scenarios. Take the middle column, where an elephant morphs into an excavator. The upper rows reveal how baseline methods like 3D interp and slat interp often collapse into noisy, scattered debris or blurry ghosts. However, looking at the bottom row, MorphAny3D preserves solid geometry throughout. It successfully blends the organic shape of the elephant into the mechanical structure of the excavator without losing definition. Well, having established the overall performance, Figure 8 conducts an ablation study to verify each component's contribution. In Panel A, comparing the top and bottom rows shows that morphing cross-attention prevents the local artifacts highlighted in the blue boxes, which appear when using simpler key-value fusion. Next, Panel B demonstrates the need for temporal fused self-attention. Without it, the bottom strip reveals flickering and instability in the crab's claws, marked by the red and green outlines. Finally, Panel C proves the value of orientation correction, because without it, the model suffers from severe orientation jumps, causing the object to spin wildly instead of morphing smoothly. So complementing those visual examples, Table 2 lists the quantitative gains from adding each component step by step. Starting with the basic key-value fused cross-attention in the first row, we see a relatively high Fréchet inception distance of roughly 125. Introducing morphing cross-attention in the second row immediately sharpens the visuals, dropping that error score down to 112. Next, the third row shows that adding temporal fused self-attention significantly cuts the perceptual path length, confirming the smoother motion we just saw. Finally, the bottom row demonstrates that including orientation correction optimizes every metric, securing the lowest scores for the complete framework. Wrapping up, 2 takeaways stand out. MorphAny3D demonstrates that high-quality cross-category morphing works without expensive training. By blending features directly within the attention mechanism, The framework maintains structural coherence that simple interpolation misses. This points toward a future of much more accessible and flexible 3D animation tools. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.